Welcome back, class. It's Dr. Linder. We are still on chemistry, your favorite topic to learn about, I know. We're going to be contrasting now inorganic compounds and organic compounds. But in this video specifically, we're going to focus primarily on inorganic compounds only. Organic compounds are a little bit more information because we're going to be talking about proteins, carbs, fats, and nucleic acids. With inorganic compounds, we're going to be focusing primarily on water. Okay. So inorganic compounds and solutions. So inorganic compounds usually lack carbon, and they're quite simple molecules. Water is the most important and abundant inorganic compound. So when I get into organic compounds, those kind of look like this, where they have a long, very long carbon chain. And then attached to a carbon chain, there's going to be hydrogens attached, right? So when you have all these carbons and they're all saturated with hydrogens, these are organic compounds when you see something like that. But inorganic compounds, they lack carbon. So it's not this at all. Okay. Organic compounds, they always contain hydrogen, though, and they usually contain oxygen, but they always have covalent bonds. We will be concerned primarily with water and how its properties are essential for life. Most other inorganic molecules are going to exist in association with water. So carbon dioxide and oxygen, for example, these are gas molecules, and how are they transported in the body? Through water. Through water. Okay. All inorganic acids, bases, and salts, all of these dissolve in body fluids as well. Water, once again, that is known as the universal solvent. So we're going to learn a few words that sometimes students confuse: solute, solvent, and solution. Okay, they're different. Water makes up about 2/3 of the total body weight. The bonds in water are oriented in such a way that the hydrogen atoms, they're held close together. As a result, the water has a positive pole and a negative pole. So water is sometimes called polar molecule because of these poles. An aqueous solution containing positive and negative ions will conduct electrical currents. We know you don't want to drop a hair dryer in the toilet bowl or put a toaster in the bathtub. You don't want to do that. Many inorganic and organic molecules will dissolve in water. When you have these inorganic and organic molecules that dissolve in water, whatever it is you're putting in here, now you have a solution. But the medium in which other atoms and ions and molecules are dispersed, that's called the solvent. So if you have a jar and this is just water, the water is the solvent. Now I'm putting in sodium in here and I'm trying to dissolve sodium in there. That's the solute. Whatever it is that I'm putting in is the solute. When this dissolves in there, now I have a solution. Okay. So here, this blue powdery stuff, that's the solute. The water, that's the solvent. When I put this inside there and it starts to do its thing and diffuse, now I'm left with a solution. Okay, so make sure you know the differences there. Here's the structure of water. So you can see you've got a negative side and a positive side. And what happens to positives and negatives? They're drawn to one another. Positives and negatives love, love, love each other. So they're held together by that hydrogen bond, but it's a weak type of attraction. It's weak, so these can be broken. But then as quickly as they're broken, then they start to form again. That's what creates the surface tension on water. Water also has a heat capacity that's really high. It can absorb a large amount of heat with only a small increase in its own temperature. Bonds are broken as the heat is absorbed instead of increasing the temperature of the water. Okay? Water also has a cohesive nature to it. It allows water molecules, it allows blood and body fluids to smoothly move through them, right? Blood has a certain degree of water in it. It allows it to move through. That's why hydration is so important. When you're dehydrated, your blood becomes more viscous and thicker. So we want to be hydrated. Our joints need water because in our joints, we have synovial fluid and it helps to lubricate our joints. We need water because our respiratory tract uses it to help produce mucus. We need water in our digestive tract. It helps to break down the proteins, carbs, and fats through hydrolysis. We need the hydration. We need it for healthy bowel movements. Okay? We need it not just for mucus, but for serous fluids as well. Where in our chest, where we have the heart and lungs, and in the abdominal cavity, where you have all of your abdominal organs, the organs need to be slippery so there's no friction between them and the organs can slide past one another. So water, water, water is very, very important. How much water should we be drinking? There's different formulations. The one I tell my patients is if you weigh 200 pounds, just divide that in half, okay? If you cut your body in half, you get 100 ounces, 100 ounces of water. If you weigh 150 pounds, then you want to be drinking 75 ounces of water. Whatever your weight is in pounds, cut it in half, and you should be drinking that in ounces. That's a general rule of thumb. And it should be mineral water, never distilled, always mineral water, never distilled. So here's water. This is just showing water as a polar molecule. Again, we have oxygen, and you can see it. There's 2, 4, 5, 6. There's only 6 electrons, and hydrogen has 1 on each. So if we bring this one here and bring this one here, now you have H2O. That's the structural formula. 2 hydrogens bond to an oxygen. That's the molecular formula, H2O, stable. Water is the ideal medium. Remember, we talked about water being involved with hydrolysis reactions and dehydration synthesis reactions. In hydrolysis reaction, water is added to break the bonds, and in dehydration synthesis reaction, water is moved. So here, dehydration synthesis, we're taking H2O here, we're removing it, we're just adding it to the other end of the equation. So we're going from glucose and fructose, we're bringing 2 monosaccharides together to make a disaccharide, to make sugar, right? Anything that ends in ose is always a sugar, but sucrose is table sugar. It's 2 monosaccharides combined. Now, if you eat a cookie or have a lollipop or something that has sugar in it, in order to break it down, we need water, and water takes the disaccharide and breaks it down into monosaccharides, and glucose is what the body can use for energy production. But in order to do that, we need to take that water. The water is added, hydrolysis reaction, the water is added to break the bonds. We put this back in. So hydrolysis and dehydration. Dehydration, synthesis, remember synthesis, we're making something bigger. You're taking monosaccharides and making a disaccharide. Hydrolysis, hydrolysis, lysis means to split. We're going to make it smaller. We're going from a disaccharide to monosaccharide, something bigger to something smaller. Now, acids, bases, and salts, in each of these beakers or each of these, there's water. Okay, the orange is water. So what we're putting in here is hydrochloric acid. When you put hydrochloric acid in water, these will break down into hydrogens and chlorine. Whenever you add hydrogens to something, remember hydrogens make it acidic. Let's remember that pH scale that goes 0 to 14. 7 is neutral. Anything from 0 to 6.999 is an acid, and anything above 7 to 14 is a base or an alkali. And we know that blood pH is right around there at 7.4, and we know the stomach pH is right around there at 2.3, and we know 2.3 in the stomach because we have hydrochloric acid. So when you put hydrogens, which are protons, into the stomach, you're making it more acidic. That's why the drugs that are used to decrease the acidity in the stomach when someone has heartburn is called a proton pump inhibitor. The proton is the positive charge, that's the hydrogen. If we block hydrogens and we don't have that, you don't have acid anymore. All right, so HCl, when it's dissolved in water, you get hydrogen and chlorine. The more hydrogens in a solvent, it does give you an acid. When you dump potassium hydroxide, it dissolves in or breaks down into potassium and hydroxide. Hydroxide is an alkaline. So that is a base. Whenever you add hydroxide into a type of solvent, it creates an alkaline or a base. Now, when you're taking potassium chloride, none of which is hydrogen, none of which is hydroxide, now we have potassium and chloride. Potassium and chloride would be like sodium chloride. It's a different type of salt. Or calcium chloride, right? That's what we use to melt snow in the winter. You put down calcium chloride. So that's a salt. Okay? These are also electrolytes. They act as electrolytes. Sodium chloride, calcium chloride, potassium chloride. Salts and electrolytes, they're not acids, they're not bases. Why? Because there's no hydrogens involved and there's no hydroxides involved. So that's acids, bases, and salts. An acid, a solute that adds hydrogen ions to that solvent or to the solution. When that happens, we have an acid. A base is when you add the hydroxide to it or you remove hydrogen. So if you add hydroxide or remove hydrogen, which is the same thing, when you're removing hydrogens, well, that's going to give us an alkaline or a base. Okay. Now, weak acids and weak bases, these are things that fail to dissociate completely. Here, we had good dissociation. These dissociate, this dissociate. At weak acids and weak bases, they fail to dissociate completely but they're involved in balancing out pH. Okay, there's your pH scale. So let's take a look. We got 0 all the way to 14. And just to give you an idea, because I understand that, people want to drink alkaline water and they say, let me alkalinize my body so that cancer cells don't live and you're healthier in an alkalinic environment. They're selling that idea to ignorant people. And I don't say ignorant like to demean the individual. Ignorance means like you're ignoring. There's information out there that you're not aware of yet. So when you understand this, you can educate people and say, save your money. Okay. With 75% of the population on some sort of pharmaceutical medication, most medications need to be taken with an acidic water. They work better that way, believe it or not. All right. Just to put it in perspective. So here's neutral. There's 7. That's neutral. There's blood. It's around 7.4. Here's ocean water. Here's bleach. Here's ammonia, right? So as you move in this direction, you're going to extreme alkaline or extreme basic. As you move in this direction, you're becoming more acidic. So your stomach acid is somewhere down here. Vinegar, beer, wine, pickles, they're all here. Tomatoes. That's why they say if you have heartburn, stay away from tomatoes because it can add to your heartburn. Here's saliva. So can you drink the so-called pH water of 10 or a pH of 13? Can you drink water that has a high pH and think that you're going to alkaline your entire body? Nonsense. The only thing drinking high alkaline water is going to do is going to go down your esophagus into your stomach. And when that alkaline water goes to your stomach, it's going to raise the pH of your stomach, good or bad, very bad, because in an acidic environment, and only in an acidic environment, that's how the body absorbs B12, iron, and calcium. So and in an acidic environment, it allows you to break down protein. Why? Because we have something in our stomach called pepsinogen. Remember, anything that ends in ogen means it's inactive. Pepsinogen must be converted to pepsin. So pepsinogen, which is inactive, has got to be activated to pepsin. Guess what does that? Hydrochloric acid. You need an acidic environment in order to convert pepsinogen into pepsin, and pepsin is the digestive enzyme that is needed to break down your proteins so that you can make neurotransmitters, make muscle, make healthy bone, make connective tissue. Well, your body is so dependent on proteins. So if you consume antacids or drink pH water, it goes in the stomach, changes the acidity, and now you're up here somewhere, which means you're not going to be able to digest your protein well. You won't be able to absorb B12 or iron or calcium very well. So hopefully that sheds some light. And also in an acidic environment, it keeps the right bacteria in the stomach because hydrochloric acid is bactericidal. It kills the bad bacteria and keeps the good bacteria. Okay, here's just another list of some of the pHs. Here's lemon juice, right? Here's hydrochloric acid, 1.2 to 3.0. So I usually say 2.3. Here's coffee. Here's saliva. Here's blood pH, semen pH, pancreatic juice, bile, and vaginal pH is somewhere up here too. Vaginal pH is up on the alkalines, right up in here somewhere. So if you change the pH of the vaginal area that should be a little bit on the acidic side by adding alkaline water, you change the pH, you're in trouble. Really big, big trouble. So to manage and buffer the pH, I know I spoke about this in a previous video, but remember that reversible reaction where buffer systems help to regulate pH by converting strong acids or bases into weak acids or weak bases. So here, this is bicarbonate. That's bicarbonate, and this is carbonic acid. So if you add a hydrogen to that, whenever you add hydrogen to something, you're going to make it acidic. So when you add hydrogen to this, you get to bicarbonate, you get carbonic acid. When you remove the hydrogen, when you take one out, and let's say you add it to water, then you get H2O and bicarbonate again. So this buffering system can go back and forth because your body is trying to go, if I'm too acidic, let's make it alkalinic. If I'm too alkalinic, let's make it acidic. Okay, it's a good place to end. When we come back, we'll talk about organic compounds.